I talked in the first lecture about gap systems, which are most of our best-known topological phases. The point of this one is to talk about gapless systems, but still at the one electron level. And then the third lecture will be very different and will be about a field theory for the fractional quantum Hall effect that can give some background for the talks you've heard about edges. So for this lecture, the main thing I want to talk about is, again, electromagnetic response, now for metals. And until recently, at least until the discovery of graphene, we would have thought that metals didn't really have topology in quite the same way. They could have, if you want, wave function geometry and Barry phases and so on, but we wouldn't get quantization in a material-independent way. But there turn out to be at least a couple of examples of things that become quantized, although for semimetals, they seem to be easier to measure in optical properties rather than transport. Now, optical properties are something that I never learned all that much about as a student. Hopefully, your education was better. So I will provide a little bit of background, but please ask if it is helpful, as Alex said. And one thing I'm going to build up to, I'm actually going to spend a while before I even get to Weil semimetals, but three different and potentially interesting effects in Weil semimetals. One is the so-called chiral magnetic effect. One is the chiral anomaly. I'm going to quickly say a few words about those two, at least what they are. But then my main focus will be a kind of chiral photocurrent. And for that, that's recent enough that it's sort of the experimental work Claudia already mentioned, and the theory work is just a couple of years old, so I thought it would be good just, I'll mention things as I go along, but in case I don't, this is very much a collective piece of work. The people at the top all passed through Berkeley at some point. Of course, Fernando de Juan and Adolfo Grushin are two of our organizers, and Claudia Felser, one of the key parts of the experimental team, is a regular at these schools. All right. So in general, when we're thinking about electromagnetic response, usually the symmetry of a material is what allows the response to be present. And there's sort of a general principle in physics that whatever is allowed to be present should be there. Everything that allowed is not just allowed, but required or mandatory. And if it's not there, then you need an explanation. What topology usually tells us is how that electromagnetic response might actually be quantized and sort of independent of microscopic details. And then a stronger sense of topology, like a world without rulers or clocks, is what happens in lecture 3 with topological field theory. So when we're thinking about symmetries of materials and how they relate to optics, if I have a material that doesn't have any center of inversion, that turns it out to be what you need for the simplest nonlinear optical properties, which are things that respond to 2 powers of electric field. So usually when we think about transport, we're thinking about linear response to electric field. When you go to quadratic order, most materials don't have any quadratic response to electric field, at least in the sort of dissipationless limit, because there's too much symmetry. But if you break inversion, then you can get things like frequency doubling or second harmonic generation. Light comes in at omega, and you get light out at 2 omega. So gallium arsenide is an example of that. But suppose you want something even better, which is that you can take your sample and you can put it out in the sunlight, say, something which is unpolarized and normal incidence, and get out a current. So a photocurrent, which is a practically useful thing, that's another example of a response that is quadratic in electric field, because photocurrent is current going like intensity of the light, E squared. But if you took gallium arsenide, you wouldn't actually get a photocurrent, because if you like, the current wouldn't know which way to go. Gallium arsenide breaks rotation, but it has a lot of threefold rotations and so on, so it doesn't have any preferred direction that the current can flow along. There are plenty of crystals that do, or if you like, when we make a p-n junction photocell, we're creating a preferred direction, the direction from, say, p to n. So polar is the subset of inversion breaking materials that actually have a preferred direction. And then chiral is a different subset, which are basically materials that are handed. So that's not only breaking inversion, but also not having any mirror symmetries. And that allows optical rotation, which is like the Faraday effect in a magnetic material. It means that light passes through, and the plane of polarization gets rotated. So when I talk about the chiral photocurrent, that's going to be something that happens in chiral Weil semimetals. So this bit, in fact, a lot of the way people understood the symmetries of crystals was looking at how light went through them. But that bit is certainly old. The new bit is trying to figure out how do the electrons in a material generate these things, and in particular, when do you get something that has the microscopic sort of drop out. But it's probably a good point to make, and this already came out in Professor Kane's first lecture, that just thinking carefully about topology has led us to be more careful about what symmetry allows and what symmetry forbids. So for example, with electric polarization, we would have said until fairly recently that inversion symmetry means polarization is zero, but now we know that in a sense we can have zero polarization or pi polarization. There are at least two different notions of inversion symmetric polarization. All right, so as background, before I get into some details, I'm going to come back to a proper definition of a Weil semimetal later on, a solid state definition. But here's why you might care. And Claudia said this very quickly, so I'll say a bit more. If you go look at what we think are the fundamental particles in nature, except maybe for gravity, there are a lot of interesting fermions, but they all have a mass and are not Weil fermions. Weil basically pointed out that if you have a massless fermion, then in any reference frame, it has the same helicity. It's either a right-handed spinning fermion or a left-handed spinning fermion, and those are totally decoupled from each other. So at least you could have fermions in that class, but we don't seem to have them as fundamental particles, but we do have them just in the last 5 years or so in materials. And it turns out that even if you don't care so much about topological quantization and so on, a zeroth order fact to take away is that tantalum arsenide, which is kind of the benchmark Weil semimetal, and does not actually have the chirality that I'm going to focus on, even that has extremely strong nonlinear optics. It has second harmonic generation that is something like 100 times gallium arsenide, which is maybe the reference. In fact, I think it has the strongest second harmonic generation in some frequency ranges of any known material. So what I'm going to focus on, because this is a school on topology, I will say maybe just a couple of words about that. If you go to other Weil materials with lower symmetry, and finding one was a bit of a story, then there's a nonlinear optical effect that is not just strong, but also quantized, and that comes from topology. But a large part of the first part of the story is going to be, why do we claim that transport and linear optics will not give you something quantized in the way of electromagnetic response in Weil semimetals? So I'm going to start with what was more or less a no-go theorem, or not exactly a negative result. We feel like we understood a lot, but saying that what had been proposed as a unique linear response effect for Weil semimetals in electromagnetism, we don't think is actually that unique to Weil semimetals. It actually solves a beautiful old problem of like what happens to light when you pass it through quartz. So that's going to be why we claim that linear optics and linear transport is not good enough. But I should be very precise. That means response to one field. So in a sense, the Hall effect is not even response to one field. It's a magnetoconductance because you've got a magnetic field on, although the magnitude of the field doesn't show up in sigma xy. So that's already an experiment with two fields. The Hall effect, you've usually got a big constant lab field and then a small applied electric field. So even that would not fit into our sort of no-go picture. So since this is a school, let me give a bit of background on the old picture. But this will also convey why, in some sense, geometry is easier, or Barry phases show up more in metals, but the way they show up is a bit more contaminated by messy details than it is for insulators. So what's sometimes described as the biggest mistake in Ashcroft and Merman, the classic solid state book from 1977, is that if you look at the semi-classical equations of motion in a metal, so things that we use all the time to make a simple description of transport in metals, they've only got the first term, and they don't have the second term. Let me explain the first term. I think you've all seen before. This is the fact that when you go into a crystal, band structure modifies the energy-momentum relation. The second term is the so-called anomalous velocity, and the idea of this goes back to at least the early 60s in work of Karplus and Luttinger, but they had a hard time convincing the community because this term, the reason they proposed it was to explain experiments on the anomalous Hall effect, and I'll remind you of what that is in a second. exactly how this behaves in the presence of disorder is still quite tricky. Although we do believe that this is important for many experiments, it isn't the kind of thing like in the insulating case where we can claim topological protection. So to explain what this is, what's going on, well, remember, this is the Berry curvature, and this is how the momentum is changing in time. And one note is that having this, we sometimes call this a magnetic field in momentum space, because having these two terms makes this equation look a lot like the Lorentz force. If you want the Lorentz force, like for example, the equation dv dt is like E plus V cross B. Well, now we've got two terms in the velocity equation as well, and this looks a bit like a magnetic field because it's got something changing in time here. So if you want a quick mathematical reason why this should be here, you've heard multiple times that polarization, the Berry connection A, is related to polarization. A change in polarization in time is a current. So this looks like dA by dk, dk by dt. So this is like a total derivative of polarization, which should be a current. And if you're wondering what is that current and how is it different from the current here, the way it's normally described is for the Berry phase to be present, I need to have more than one orbital in the unit cell. Suppose I've got two orbitals in the unit cell, A and B, and suppose they're at different locations. And then maybe at one momentum, the block state is concentrated on orbital A, and then at a different momentum, the block state is concentrated on orbital B. Then what happens is the momentum is pushed from the first value to the second value by an electric field, say. Well, then the electronic wave function, in addition to this kind of group velocity piece, there's another part, which is because it's moving inside the unit cell. So if you like, the group velocity is what the electron would have just as a point particle, but this second piece is because the electronic wave function has some structure in the unit cell, and that structure changes as a function of momentum. So that's why this term pretty much has to be there, at least in a complicated enough crystal. And as I said, it was originally explained, introduced to explain the intrinsic anomalous Hall effect measured by people like Hall a long time ago. And then it turns out to explain some optical measurements as well. But until quite recently, our thought, at least my thought, was that this term, it might underlie a lot of important physics, but it wasn't going to give you quantization. And I'll kind of sketch why. Yes, question? It's there in 2D, but not in 1. That's right, because in 1 there is only A, there is no F. But yeah, there is a 2D version. That's right. So that basically this term seems to be important for a lot of transport and optical phenomena, but most of the time it doesn't give you something quantized, basically because the Fermi surface of a normal metal is something that you can deform smoothly. You can make it smaller or bigger, and most physical things change. But what about semimetals? Semimetals, maybe the Fermi surface is a point or something like that. So semimetals, that's already a clue, might be a little bit special. But you'd say, well, having the semimetal Fermi surface be a point, like in graphene, that's only true because you got the Fermi level in the right place. What if the Fermi level is perturbed a little bit? And that's kind of an argument for why you should go to optics and finite frequency. But the punchline is going to be that in semimetals at non-zero frequency, you get at least two pretty interesting things. So this is my brief history of the anomalous Hall effect. So Hall not only took normal metals and put them in a magnetic field, he took things like iron that are magnetic by themselves. Sorry. And he measured sigma xx and sigma xy. And what happens if you take a metal like iron, and I'm not going to talk a great deal about disorder in the anomalous Hall effect because it's a hard and complicated problem. My only evidence that it's hard and complicated would be that after figure 47 of a very good review article, it's still only a speculative and schematic phase diagram. So this is not an easy problem to approach very quantitatively in real materials. I'll tell you the best experimental evidence in a second, but the idea, what we now believe, is that if you take a metal like iron, if you make it very clean, so this is high conductivity and low conductivity, if it's very clean, then your normal picture of the Fermi surface is important and scattering at the Fermi surface is important works. So we say that things are dominated by the details of disorder and the shape of the Fermi surface and so on. If you make your material very dirty, you get dominated by localization physics and things like that. But there's a big region in between, say 3 orders of magnitude in conductivity, where it seems like things are dominated by what we call the intrinsic piece of the anomalous Hall effect, which is this. So this is the exact same integral that Tk and n we're talking about. If I integrated over the whole Brillouin zone, then I would get, at least for a 2-dimensional Brillouin zone, say, I would get the Chern number, and this would be quantized. This is saying, well, in a metal, instead of integrating over the whole Brillouin zone, only integrate over the occupied part, the Fermi sea, and you'll get something that, well, now you're trying to do an integral of geometry, but it's not over a whole closed torus, it's only over some arbitrary piece of the torus, so it won't give you an integer. It'll just give you some number times e squared over h. But we still think of it as intrinsic because this part cares only about the band structure. It doesn't care about the details of disorder. Well, if I go to the very clean limit, then it actually cares about what kind of impurities are causing scattering and so on. So if you like, this is an intrinsic or scattering independent piece of sigma xy. And one really nice piece of evidence that this works was actually done by Ivo Souza, who's here in Donostia, theoretically, which was to compute, take a magnetic material that is anisotropic, so x is different from y is different from z, non-cubic, and calculate what does the sigma xy tensor look like, that is sigma xy, xz, etc., if it's coming from the band structure. So you can make a prediction of what would be the anisotropy if the Hall conductivity is dominated by this intrinsic piece, and then you look at the experimental data, and it agrees very well with what you'd expect if the intrinsic piece is dominant. While the scattering-dependent piece, that's more Fermi surface, whatever that is, that should have a different anisotropy than the Berry curvature piece. So that's one way you can sort of check experimentally that this phase diagram is probably right. But as I said, with disorder, it's a hard problem. So we were motivated, this is a few years ago, Joe Ernstein and me, to try to find easier Berry phase effects where maybe the role of disorder would be a little bit simpler. Even that turns out to be hard, but let me just give you an idea of a Berry phase effect in optics, but why in low-frequency optics, which is kind of like transport, you don't get anything very different, if you like, in spirit. It's still controlled by sort of the details of the Berry phase. So this effect is going to come back later. It's called the circular photogalvanic effect, or in a 3-dimensional version, you can call it a chiral photocurrent. So in the simplest case, it's a 2-dimensional effect, and this was measured for many years by Ganichev and Regensburg on a whole variety of quantum wells that are very clean. And the idea of it is the following. I'm going to look at a photocurrent induced by light, and in particular, the piece of the photocurrent that cares about whether the light was right circular or left circular. So a photocurrent that is one way for right circular and the opposite way for left circular. And you can do a symmetry analysis of that and find out which inversion breaking or whatever crystals allow it. But here's the simple picture of why this is a good thing to look at from the Berry phase point of view. Basically, the ordinary velocity, whatever it is, drops out, and you're only left with the anomalous velocity, the piece that involves the Berry phase. So the idea is just think about your low-frequency semi-classical picture of transport, where the ground state electron distribution is the black circle. I push on that with the electric field of the light, and eventually I reach some equilibrium at DC where the current carrying state has the electrons pushed a bit to the right. So now low-frequency circularly polarized light, omega much less than 1 over tau, will kind of slowly rotate the gray circle around. And then it's pretty easy to show that the ordinary velocity averages to 0, but the anomalous velocity doesn't need to average to 0 if you have a low symmetry crystal where one way to do it would be to have the Berry curvature linear in K near the gamma point. Because when I go from, say, the circle on the right side to the circle on the left side, dk by dt flips, but so does the Berry curvature. So anyway, the anomalous velocity does not average to 0. And I think that of this theory is basically successful because you can go back to many years of experiments that were interpreted differently in terms of things like spin-orbit coupling and say that if you use this very simple Berry phase semi-classical theory, you get a certain magnitude, and that seems to explain the experiments quite well. But it's very material dependent, so not particularly topological. So then we got interested in another problem where, without even knowing it, we were working on wild semimetals. And I'll tell you what we thought we were doing, just for one slide of maybe conventional condensed matter motivation, but it turned out that the problem we were sort of studying, I'm going to focus on point 2 here. We were studying an old problem, which is how do materials rotate light, but that is nothing other than the so-called chiral magnetic effect of wild semimetals. Although, to be precise, there are 2 versions of the chiral magnetic effect. One is easy to remember because it's 0. I'll try to explain briefly why. And then there is a version which is non-zero, the dynamical or transport or whatever chiral magnetic effect, but the version which is non-zero is actually the old problem of linear optical rotation. But this is what I meant by kind of a no-go theorem, because I'm going to go through a couple of slides to explain why linear optics does a lot of very interesting things. And in fact, the simplest example of a quantized linear optical property, to me, is about the most elegant experiment that you can do with your hands, and it is, I think, the shortest paper I know in Science magazine in recent years. So linear optics is great, it just happens not to be great for wild semimetals. It's good for some 2D semimetals. So the problem we cared about, just for your general condensed matter education, is still a mystery, which is that if you look at the high temperature cuprates, there's a region where everyone agrees now that something interesting is happening. In fact, this red dotted line is the biggest change in this phase diagram since I was in grad school, 2 decades or so ago. Now we believe there's some kind of charge order, like a charge density wave, that onsets here. And almost everyone agrees that what's happening, say, is that if you started with the square lattice, you're breaking the symmetry of the square lattice down to the symmetry of a rectangle. However, one respected group at Stanford, Aaron Capitonic's group, sees a signal here that is only explained by time reversal breaking. But we were wondering, could that signal possibly be explained by complicated kinds of charge order and so on? And the answer seems to be no, in our opinion, but after several years. But I think this remains a puzzle whether there's only charge order here or actually something like magnetic order that breaks time reversal. So that's why we cared about optical rotation, because the measurement, the Kerr signal that they measure onsets at the same place, but is a different effect. Very briefly, here's what the Kerr effect is that they see. You bounce light off your sample, and they can measure the degree of rotation of the light by nanoradians, by some clever interferometry. So it turns out that if you have a material that is time reversal symmetric, there is no rotation in linear response. This was, I think, shown clearly by Bert Halperin, and then rediscovered more recently. But I think the Halperin paper from the late 80s is really good. But if you pass light through the material, so what I'm going to focus on starting soon is passing light through the material, you find that even chiral non-magnetic materials rotate light, and how much they rotate is pretty interesting. So this is the long puzzle I mentioned, that basically if you have time reversal symmetry, then I think it's now accepted that however complicated the charge order, even if it's chiral, you can have the equivalent of Faraday rotation, which is rotation in transmission, but not rotation in reflection. And if you're a very precise optics person, you would reserve the term Faraday rotation for magnetic materials, time reversal breaking materials, and you would call it natural optical activity or gyrotropy if you were talking about a non-magnetic material with chirality, like quartz, sugar water with chiral sugars, whatever. So anyway, that's a little bit of history. So here's how that all connects to the chiral magnetic effect and what we call the gyrotropic magnetic effect. So I'm going to tell you what a wild semimetal is in a moment and lead up to this formula at the bottom. So this is an outline of where we're going in case the pathway is not clear. So the idea, I'll tell you what a wild semimetal is and why people hoped that in a sense there would be a current created linearly by a magnetic field. So this was the chiral magnetic effect. It's different from the chiral anomaly, which involves both E and B fields on the right-hand side. So one fact, which wasn't so obvious at the beginning, but I think I can show you, I think now people have been convinced, is that at equilibrium, you don't generate macroscopic transport coefficients just by putting a magnetic field on something. That's a big difference between B fields and E fields. A system can reach equilibrium in a B field with no current, but not in an E field. Anyway, so at equilibrium this is 0, but then people had the idea that if you want to make something non-zero, maybe you should slowly oscillate the magnetic field. So that was going to be the dynamical chiral magnetic effect, say. But the problem is if you slowly oscillate a magnetic field, you create something known as an electric field. And that combination is basically a light wave. And if you figure out what this effect is describing, it's basically describing optical rotation of a light wave passing through a material, which is a 100-year-old problem. But what you realize in trying to sort out how that happens is that there's a second problem in the semi-classical equation of motion. There's another thing you have to include, and the key ingredient is the orbital moment of Bloch electrons. And I'll tell you what that is in a moment. It's actually not that different from some of these Berry phase things. A little bit less geometric, but still very wave function dependent. So that's going to explain this optical rotation quantity, or the gyrotropic magnetic effect. So this formula is going to be the punchline that I try to justify. So first, here's why it's not crazy to think that something in a semimetal might be quantized in linear response. So this is the experiment I said I like, which is the only downside is you need a big sheet of graphene. So you need a friend who has access to a big sheet of graphene, but if you can get it, you can hold it up to the light, and you can ask how much light gets through. And if you've ever seen a picture, most of the light gets through, but in the visible, about 2.3% of the light does not. So it's mostly transparent. A little bit of light gets blocked. That 2.3% is not an accidental number. It's pi times 1 over 137, where 137 is the fine structure constant. And the point is, that's the fine structure constant in vacuum. It doesn't involve the velocity of graphene. It involves the velocity of light in vacuum, or air maybe. So this 2.3% is not 1 part in a billion. It's more like 1 part in 100. But this is, if you like, the existence proof that things can be pretty well quantized, even in semimetals, even in the real world, even with the naked eye. So in other words, if you stack together a few sheets of graphene, you could figure out how large the fine structure constant is just by counting how many sheets of graphene you needed to reduce the light intensity by 2. So that's why I like this experiment, and it was pointed out by Andre Geim's group in a very short science paper soon after the discovery of graphene. So the downside of this is it's not particularly topological or well protected. It happens at some range of frequency where it depends on the linear slope of the bands in graphene. So if you go up to high energy, it won't work. And if you go down to low frequency, it won't work because you wind up being dominated by disorder. But at least this is a clue that maybe in some frequencies, and maybe by adding topology, you could get something a bit more protected. So could there be an interesting analog of this in three-dimensional Weil semimetals? I think that was worth thinking about. So what is a Weil semimetal, since that term's been thrown around a couple times already? So very quickly, go back to the early days of quantum mechanics, and Dirac had this 4x4 matrix equation that we think is still a very good description of the electron. So in our language, a 4-band equation. If you don't have a mass, then you can break that up into 2 separate 2x2 matrix equations. In our condensed matter language, we would say we need to either break time reversal or break inversion. And in this talk, unless I say otherwise, I'm going to be talking about Weil semimetals that break inversion but not time reversal, because at the moment we have more of those. So right after Dirac, people figured out 2 ways to simplify his equation or break it up by making additional assumptions. One was Weil's, which is that you have massless particles with definite handedness, and the other was Majorana's, which is that maybe you have particles that are their own antiparticle. So it turns out that Weil fermions in particle physics are almost exactly the same as Weil fermions in condensed matter, while Majorana fermions in condensed matter shouldn't even really be called that. They're totally different from Majorana fermions in particle physics. I have 1 or 2 slides on that in the end, but if I don't get to it, Majorana fermions in condensed matter are sort of a way of labeling degenerate states and so on. They're always 0 energy and so on. They're very different from Majorana particles like possibly the neutrino. So here's what a Weil semimetal looks like in condensed matter. And again, theoretically, the idea of a linear 2-band crossing is very old, but topology did add something. And helium added something also, I should say, in fairness. So the old idea, in fact, Conyers Herring was a great condensed matter theorist, and his PhD, I think with Wigner at Princeton in the 1930s, was on Weil semimetals. So they're even older than graphene, if you like. Graphene was 1946, and Weil semimetals were 1937 or something in solids. Our modern language would make the following point about two-band crossings and why they're special. So again, I can use my Berry curvature from before. So if I look at one of these two-band crossings, near which I have Weil fermions, I can make a little sphere in K-space. So a three-dimensional sphere with a two-dimensional surface in the three-dimensional Brillouin zone around that Weil point. And I find that the Berry flux close enough to the point is either like a monopole flux out or a monopole flux in. And the charge of that monopole, in other words, the integral of the Berry flux around the little sphere around a Weil point, is quantized. Because again, remember, so we had that A was some A was something with one derivative. F was curl of A. So F's got two k derivatives in it, which means we should integrate it over a two-dimensional surface in order to make something dimensionless, maybe quantized. So in 3 dimensions, you have two choices. You can't use the whole Brillouin zone anymore. You can use a two-dimensional cut of the Brillouin zone, or you could use a little sphere. And the little sphere around a Weil point is an example of where you can use this concept, this Berry curvature, even in 3D. So there is a surface state analogous to the surface state in helium-3A, which is very important in how these materials were discovered. The Fermi Arc State in this paper by Juan Turner, Vishwanath, and Savrasov, if I remember, is the following idea. If I look at the surface projections of these Weil points, let me go back to the 3D topological insulator. The 3D topological insulator basically had half of a normal metal on the top surface and half of a normal metal on the bottom surface. A Weil semimetal kind of does the same thing, but it cuts the normal metal in a different way. You've got one arc of the Fermi surface up on top of the material, and then the Fermi surface closes on the bottom of the material. And there's a pretty spectacular experiment. I actually saw a poster related to it by James Annelidis and collaborators, which is looking for quantum oscillations. As you probably know, in a quantum oscillation, the electron moves along the Fermi surface. So what can it do when the Fermi surface ends? Well, the quantum oscillations, or the Weil wiggles, I think is in the title of the paper maybe, they start on the top surface, they hit the end, they move through the bulk of the material, finish the orbit on the bottom, and then come back up to the top. At least that's what the experiment is claiming to see. So there are pretty dramatic consequences of this surface state. I'm actually going to focus on bulk responses for the rest of the talk. So the good news is, because Weil fermions had been thought about for many years in particle physics, even if they turn out not to have them, they did think about some things they might do, and the most famous is the so-called chiral anomaly, which is one way of understanding why we never find just one Weil point in a crystal. We always find some, oh yes, question.
Sorry, but I don't really understand what is Fermi Arc.
So normally, if I've got a metal that has a Fermi surface which is closed, so this is like, if I'm thinking about a surface, so when I say Fermi arc, now I'm talking about the surface Fermi surface, meaning the surface of the material is two-dimensional. Suppose that is a good crystal, then there's a two-dimensional Brillouin zone on the surface. And if we had a normal material, well, okay, maybe there's no surface state, but if I took a normal surface state, it would be something that is closed, like a circle. So this is what you might see in photoemission. A typical surface, Fermi surface, is a normal two-dimensional Fermi surface. It's closed. So this, what I'm drawing here is the 2D surface Brillouin zone. So what happens in a Weil semimetal is quite remarkable. Instead, so you might have ordinary surface states as well, but there's at least one Fermi surface that looks like the following. It appears to end, which we would have been very suspicious maybe was even possible. So this would be on the top of of the 2D of the material. So let's say I've got a finite sample which has a top and a bottom. If I went down to the bottom, then I get the rest of the Fermi surface, would be the way to think about it. So in a sense, if I look at the sample as a whole and think about it as a two-dimensional material, because now let's say it's finite in the z direction but extended in the other two directions, then it does have a closed Fermi surface. It's just that the states are localized in different regions. Some of them are localized on the top and some of them are localized on the bottom. But as a two-dimensional material, it does satisfy all our requirements. It does have a closed Fermi surface. It's just that they got spatially separated. And that's you can see how this was an unexpected prediction. Most materials don't have this, but materials like tantalum arsenide do seem to have it. Yes? I don't know if, I think they usually have to glue the sample down to prove I don't know if they've taken one sample and looked at the top and the bottom, but I'm pretty sure that with high confidence, there is both an arc on the top and an arc on the bottom. Yeah.
So are there actually experiments that have somehow managed to look at both?
Well, this quantum oscillations experiment is more or less seeing both the top and the bottom together. So this is a Nature paper. I mean, it's not, and there is a poster, so I forget, sorry, all the names on the poster. Philip Moll was also involved. Was it yours? So yes, introduce yourself and tell people, and I will tell people to see your poster, okay? So you can learn more about that experiment there. But the idea is, one reason why this looks like a paradox is that, quantum oscillation, the reason why that's a good measurement of Fermi surfaces is you put on a very strong magnetic field, electrons do little orbits in the field, they move along the Fermi surface, and normally that's a closed loop. Here, it doesn't look like a closed loop, but the answer is it has to move through the material and wind up on the other side. At least that's the interpretation in the original experiment. Yeah.
For a time reversal system, if you're breaking Moss metals, does it need to have magnetic order? Otherwise, like how high of a field would you bring like these particular oxide metals to break the distance?
Well, that's a good point. Yes. So if you start, okay, so some Weil semimetals are made by nature in the crystal, and others, including some used for experiments like this, are produced by starting with a Dirac semimetal and applying a magnetic field to break symmetry. And then you get small arcs, if you like. So as far as, I think it's probably hard to make a magnetic field large enough to get a splitting that is comparable to the size of the Brillouin zone, but I don't really know a number. You mean the question of how much do the... As far as I can tell, yes. But I'm not, I'd have to think about it if there's some reason why things cancel. But as far as I can tell, it's material dependent. Yeah. Good questions. All right, let me move on quickly. So we want to find bulk consequences. And please tell me when I have 10 minutes or so left. So what we're going to try to motivate is that we're going to need to go to second order. And let me just give you a power counting. It's OK if I don't finish my lecture today. I've got one more. A power counting argument for why there might be interesting effects of this type. Because I'm going to argue that, so this, as I was saying, the total charge of Weil points in a crystal is 0, which is good, because otherwise you would violate charge conservation. They might be at different energies and so on. I just mean the total charge of all the Weil points over all energies, the whole Brillouin zone, has to add up to 0, which is good because otherwise, the reason why this is an anomaly is that if you applied parallel E and B fields, you would spontaneously create charge, which would violate a lot of things we think are true. So, but what we might be able to do is something like the following. If we take the quantum Hall effect and ignore indices, we could write it that a two-dimensional current density is like E squared over H times electric field. If you just count dimensions, then if you want one more power of electric field, you could have a three-dimensional current density changing in time, going like E squared E over H times EE over H. And the remarkable thing is that some effects like this do exist in the right 3D Weil semimetals. Another way you could try to do it would be dn 3D dt would look like EB. So That's why I don't think there's some infinite list of measurable high-power quantized effects, but at least you can sort of see how if you wanted to add one more power of electric field, this is kind of a natural quantity to think about. But first, why can't we just find something linear, interesting E squared over h? Well, this was the idea of the chiral magnetic effect. If you want a little exercise to show that it's true, semi-classical equations of motion are very useful when you put in the Berry phase. Here, the Berry phase is called omega. If you do the semi-classics and you combine all the different terms, which is a little bit tedious, you get a sort of topological identity that tells you if you put on a magnetic field on any material, while semi-metal or not, and let the electrons reach equilibrium, there is no macroscopic transport current flowing, which is probably a good thing. I think we'd always assume that was true about solids, and it's sometimes called Bloch's second theorem, although I never was able to find the paper. But we think there's no effect in equilibrium, and if you want, you can do some topological exercise to prove that. More details on the exercise. We decided that we should do it quantum mechanically, so this is the first of 8 pages of supplemental information that reach the same conclusion as about 4 lines of semi-classics. So this is all just, if you're skeptical about semi-classics, like I sometimes am, sometimes it works pretty well and saves you a whole lot of time. So then what people realized, okay, so let's say everyone agreed that the effect was 0 at equilibrium as of a year or 2 ago, was that you can try something else, and this is based on an important fact that is often forgotten, even just about electrical field response, which is that when you take electric fields and apply them to a solid, the Q goes to 0 and omega goes to 0 limits don't commute. One of them, if you take Q goes to 0 first, you get conductivity, which is what you want, but if you take omega goes to 0, you get compressibility, which is an equilibrium property. If you want compressibility is apply some electric ripple and let the system reach equilibrium in that ripple. And the second one, the uniform limit, is what we really think of as transport. So the same thing is true for magnetic field. And if you like, the statement that the original reaching equilibrium in a B field gives you 0, that's like the compressibility limit. So what we really want is the transport limit. And if you do that, that's a time-varying magnetic field. And it was known that that could give you a non-zero response, but it turns to come out from the magnetic field coupling to the orbital moment of Bloch electrons. And again, you can do an 8-page quantum calculation, or I'll tell you very simply about what the entire chiral magnetic effect is, or indeed optical rotation at low frequency. It's the following other omission in the semi-classical equation of motion is the physical picture. So I never really thought about this much, but people in other communities think about it more, like the electronic structure community. When you make a Bloch state, you're building it out of some orbitals. We know that those orbitals, they might be p or f or whatever orbitals, they might have orbital angular momentum. So if I make a Bloch state out of them, that probably has orbital angular momentum as well, which is this object. Note, it looks just like the Berry phase, except that it's got an extra power of energy inside. In fact, in one of our earlier papers, for 2 bands, it is exactly the same as the Berry phase. So we thought we were seeing the Berry phase, but actually we were seeing this, which was pointed out in our later paper, again with Ivo. So this object modifies the physics in a very simple way because it can depend on k, which means now go back to the group velocity. The thing we all do remember, the group velocity, gets modified in a magnetic field because the energy in a magnetic field is this part, but there's also the orbital moment dotted into B, and the gradient of that will give me some extra piece of velocity in a magnetic field. So in other words, when you add a magnetic field to a material, you don't just push on moving electrons. There's actually a sort of moment coupling. It's almost like a Zeeman effect, but not to spin, but to orbital moment. And that's k-dependent, so that gives you some extra velocity in a magnetic field, and that's where optical rotation comes from. But it's not very special to wild semimetals. You can give me any chiral metal at low frequency, and it will optically rotate based on the orbital moment at the Fermi level and the velocity at the Fermi level. So that's optical rotation at linear response. So now we should think about beyond linear response, because that's saying that wiles are not particularly unique. And there is various transport experiments, flow case stuff, et cetera, that I don't want to get into. But here's what I mean by saying that wiles are not particularly unique. Even if you took the simplest model you could make of 2 Weil points and asked how large is the optical rotation, looking for something like graphene maybe, The problem is you're in 3D, so there's a unit-full factor, which winds up being just the distance and energy between the Weil points. So you won't get optical rotation that is quantized in a material-independent way at linear order. So you need to go to nonlinear optics. As I said, at around the same time we were working on the theory, it was found that ordinary nonlinear optics like second harmonic generation was very strong in some Weil materials. What we believe is that the circular photogalvanic effect is not just strong, but effectively quantized in some class of Weil semimetals. And because do I have 10 minutes or so, or how much do I have? 3 or 4 minutes. So you encourage them to ask more questions, which is great, but it somehow seems to mean less time for me. Come on. All right. I will skip over what we think is going on. So tantalum arsenide, just to reiterate, does not have chirality. So it's not going to have the effect that we think is quantized. It does have interesting behavior in nonlinear optics, but we actually suspect that it's not directly related to Weilness. It's related to something else, which is that it's a very strongly inversion-breaking material. If you like, the intrinsic asymmetry of the Wannier functions is very large, as measured by their third cumulant, or skewness. But if we go to lower symmetry Weil materials, then we can get a different effect, the same circular photogalvanic effect, but at non-zero frequency, and that one can be quantized. So here's how it works, and this is the theory work I mentioned with Fernando Adolfo and Takehiro Morimoto. So if I have a low symmetry Weil semimetal, then I'll have positive Weil points at some places, positive energy Weil points compared to the Fermi level, and some negative. Those behave differently under optics at finite frequency. If I've got a Weil point that is way below the Fermi level, so here yellow are the optical transitions, then these optical transitions are forbidden because I can't go into an occupied state. I will get transitions up here, but this turns out to be basically the old semi-classical effect that we'd studied before. The magic happens when I look at optical transitions across a Weil point, and those turn out to give a very strong chiral photogalvanic effect, or chiral photocurrent, with surprisingly few free parameters. I'll put it that way. All that matters is the topological charge of the Weil point, and that's a remarkable thing, if you like, because when you start off writing perturbation theory for this optical transition, you don't have anything at the Weil point. You've got states some distance away. But the magic of topology is that what's going on around a Weil point knows that the Weil point was there. So by massaging energy denominators like tk and n, but more complicated because it's nonlinear, these guys were able to show that something magic happens, which is the rate at which you put in current, and in particular, the difference between right circular and left circular is, in the right units, E cubed over h squared times electric field squared times the charge of the Weil point. To be precise, the difference in Weil charges above and below the Fermi level. So that was the theory prediction, and we were not the first people to think about what photocurrents are like at linear points. In that original paper, we had a couple of material candidates, which turned out to be hard to make in crystals and not to have large enough Weil splitting. So I want to mention 2 papers between what we did in 2017 and the new experiment that were really important. One was an experimental paper by Zahid Hassan's group finding this rhodium silicide, and the second was a theory paper. This has a lot of authors. In fact, I believe 4 organizers of this conference are on this paper. I'm not on it, so I can say it's a good paper. But it studied this material. You know, they caught on that this was going to be an exciting material, and they studied it very thoroughly, both for linear optics and for nonlinear optics, and they understood why this is a special sort of multifold Weil fermion. You get an extra factor of 4 in this equation, but otherwise it should work pretty well. Where working pretty well means, I'm going to skip this in the interest of time. This is another.
You asked me to send a signal 10 minutes before, so now it's 10 minutes before closing.
Really? I thought you just said it was 2 or 3 minutes before. Okay.
I got the algebra wrong. 10 minutes mistake. Sorry.
Okay. Yes.
Yeah, so you have more time, including questions.
Okay. Then I will go back and say one word about this in that case, which is if you want a simple argument for why you get all the material-dependent factors canceling out, let me give one, which is a result that's known for linear dispersion. So this is not going to explain the topological aspect, which is a little more complicated, but it will explain why you don't get any material-dependent parameters. It was known for a linear-dependent E versus K that the linear optical conductivity looked like E squared over H times omega over V Fermi at the wow point. So that means you're putting energy into the system if you have a real part of the conductivity. Whenever you get something quantized, it means that something is perfect. At least there must be a limit where something is perfect. So where you get the quantization is when every bit of energy that's coming in, that's dissipating here, is generating a transition across the wow point, because that change in current that induces has a factor of VF in it, so that cancels out the VF that was there. So if you like, you have a cancellation between the velocity change induced by the current, which goes up if VF goes up, but the rate of absorption goes down if VF goes up. The main point I would make about how this is different from the graphene case, aside from being nonlinear, is that if you band the bends, if you change the chemical potential at least within some range, if you bend the bands, I think I said that wrong, then it doesn't change the answer as long as, at least in some window of frequencies. And again, in semimetals, because of the sensitivity to disorder and other things, I don't think there's any reason to expect part in a billion quantization ever. I'd love to be wrong. If you can get part in 10 quantization, you're a happy camper. Here is a somewhat more sophisticated derivation of how you can start off with optical transition matrix elements, in particular the elements between the lower and upper band of the velocity operator, and write that ultimately in terms of a Berry flux from the monopole that's inside. In particular, you need to add together all components of the second order tensor, which happens to be nice in cubic crystals like rhodium silicide. So here's the sketch of the experiment that Claudia talked about, and this is on the archive if you want more details. You're sending in a pulse of terahertz light. You're sending in a pulse of high frequency light, but with an envelope that is, say, a picosecond long, which corresponds to terahertz frequencies. So if you had a very long envelope, this would be like a constant intensity, and that would give you a constant photocurrent. Now, because this is a short pulse, it gives you a pulse of current, which turns out to be into the sample, for about as long as this pulse was. And you can measure that little burst of current gives you a radiated pulse at much lower frequencies. That one is in the terahertz. And the key prediction, I would say, even aside from the magnitude, which is harder to measure, the prediction of that rhodium silicide theory paper by Felix Flicker, Adolfo, Barry, Maya, Fernando, others that I can't remember, some group of people, but what they said was, and this is nice because it was before the experiment, which is the best kind of theory, the range at which you see the quantized plateau in frequency should go from 0 up to about 0.7 eV, and that's when you start to pick up the other wild point and it should drop off. So then you look at the experiment, and I would say in the experiment, this magnitude is at best, consistent with the quantized magnitude, but there are enough factors that go into extracting what was the strength of the current pulse that the magnitude, it's the right order. It's, maybe plus or minus 50% or something, maybe 10% if you're optimistic, but it's not 4.0000 something. And here, to stress that, the later version of the figure has arbitrary units. But the magic is that it drops exactly where it's supposed to. So it's flat, more or less, until the laser pukes out at low frequency, then it decreases. And that's what we think is the evidence for this quantization of the photocurrent. So again, to estimate the magnitude, all you need to know are E and H, and the fact that the Weil point has effective Weil charge of 4. So I'll say a little bit more about that in concluding. Let me skip. The reason why I find this kind of interesting, so if you make a list of quanta and electromagnetic response, the oldest really precisely measured one is actually the Josephson frequency quantum, which is related to flux quantization, and that's an E over H quantum. There are many E squared over H quanta. Quantum Hall effect was the first, and then point contacts, one-dimensional wires, magnetoelectric effect, whatever, quantum spin Hall edges. Graphene optical transmission, if you're careful, there's an extra power of C, I suppose, but it's also an E squared quantum. And then as far as I know, in electromagnetic response, the first E-cubed quantum is this one. And this was a nice combination where there is a theory concept, but there is a lot of work in actually making it happen, both in terms of optics experiment and in terms of materials design. So it was Claudia Felser, her group made the material, and Darius Torchinsky and Joe Ornstein did the experiment. And right now we're trying to find other material examples and so on to see and say more about that. So I wanted to wrap up with 2 minutes?
Yep.
Okay, so one last comment on the other way of taking half of the Dirac fermion, because this is actually going to lead into what I cover in the third lecture, which is otherwise completely different from today. And will be on the chalkboard. So Majorana had his own way of taking half of the Dirac equation. This is symmetric theory of the electron and the positron. The electron and the positron are not actually symmetric because the electron has negative charge. You can blame Franklin for that, I guess. And the positron has positive charge, so they're clearly different particles. The neutrino is possibly the same thing as the antineutrino. We don't have any clear evidence that they're different, so it could be that in beta decay, this is actually the same thing as if you don't write the bar. But it's just otherwise an ordinary massive particle. It has no complicated statistics. It has no non-abelian statistics. Certainly, it can have a mass and so on, while Majoranas in condensed matter are really different things. It's probably better to call them Majorana zero modes or something, because they're always at zero energy. They're basically labels of degeneracy. So what I mean by that is, as you saw, Steve did this calculation from Reed and Milovanovich, which was very nice, showing that if you have n vortices in the system, it's like you have n over 2 two-level systems. So there must be something like square root 2-level system inside one vortex. That's the Majorana by counting. What I want to talk about next time, and I'm not going to do Majoranas because those are complicated, I'm going to do the abelian quantum Hall states, but with abelian particles that are not fermions and bosons. So these are abelian anyons. And I think this will also help maybe clarify some of the things you heard about from Moti Heiblim. Is that me? Okay. But in general, fractional statistics, so far you've heard about fractional particles, but I'm going to focus in the last lecture on fractional statistics because to me, one of the most amazing of many amazing things about the quantum Hall effect is, precise quantization is nice and all that, but when you go to the fractional quantum Hall effect, you realize that the most amazing thing you learned as an undergrad is wrong, at least one of the most amazing things, which is that all particles are either fermions or bosons. Because if you're in the right 2D system, you can make particles that have other kinds of statistics. How we write that as a theory, how we capture that in a field theory is the point of the third lecture. So if you like, and again, I can't do Majoranas, but I can do the Laughlin state. And it turns out that we know that Landau-Ginzburg theory captures theories like the Ising model or superconductors, things with an order parameter. What kind of theory captures the Laughlin state? It turns out that one theory gives you fractional statistics, topological degeneracy, edge modes, various other things. And that's what I want to try to do on the blackboard tomorrow. So, thank you. So here, what's going on, if I go back to the picture of the two Weil points, in order to get the quantized, if you like, the quantized value is coming from one Weil point. As the frequency goes up, it starts to become possible to have transitions across the other Weil points. So if you like, the way I've drawn it here, at this frequency, transitions across this Weil point are blocked because this one is buried. But if I increase the frequency, then I start to see both the positively charged point and the negatively charged point, and they cancel each other out. So that's why, seeing it vanish is a sign that this is coming from one Weil point, and then when you hit the frequency where the other Weil point is present, they have opposite sign, and it should go to 0. So that was kind of the prediction. That was the smoking gun from the Flicker et al. Paper. Oh, Barry.
So let's comment more of a historical curiosity. So if you look at Herring's 1937 paper where he looks at accidental degeneracies, he doesn't
I did not know that. That's interesting.
So what you talk about is it a pure bulk phenomenon, or does it have to do anything with the surface?
We think it's a pure bulk phenomenon. So yeah.
Okay, so these experiments would work no matter what the surface is or how.
It shouldn't be, that's right, it shouldn't be as dependent on surface quality as something like photoemission. That is correct, yeah. I mean, what's true is, so if you like, the while point is giving you some large and approximately quantized value. Any other bands in the system will not give you strictly 0, but they tend to give you corrections at the scale of a few percent. So that's one reason why I hope my co-authors agree. I don't think we're going to get, extremely precise quantization. You won't use this as like the benchmark measurement of electric charge or Planck's constant anytime soon. But I do think it's a very clear way to probe the existence of while points. The only problem is if you have a material like tantalum arsenide or something, you need to have positive while points and negative while points at different energies. If at every energy there are just as many positive and negative while points, which is another way, that's what happens actually in a non-chiral material, then this won't work.
All right, I guess we better get this one.